Thank you for agreeing to give us more of your time. I should say, by way of introduction, that again I am standing in for Anne Harrington. You should assume I am her. But also I am performing another function. Yesterday, Your Holiness, there were some unfortunate remarks between Arthur and Richie about the relationship between physics and neuroscience. There was the hint of competition between them. And we do not wish this to go further. So
we never thought that. I think that's the Western mentality.
So I should anyway explain that yesterday I was speaking a little about the history of the brain sciences. Today I'm chairing a session on quantum mechanics, about which I know very little. So perhaps this will help to seal the bridge between these two fields. So without further ado, I want to just make a short remark about this subject that we will spend this morning and this afternoon discussing. It is a subject, quantum mechanics, which has been present in the Mind and Life dialogues, I think, from the very beginning. And I know, Your Holiness, you have been particularly interested in this area of science for many years and have had the benefit of speaking to quite a number of physicists about this. Today we have two colleagues who are going to be particularly involved in the first session, and they will join us again with Thupten Jinpa in the afternoon session. I do want to just observe this is, especially for those like me who are not physicists, this is a tough area of modern science. There is a famous remark by the Nobel Prize-winning physicist Richard Feynman, who was an authority in this field during his lifetime, who once said, "Anyone who says they understand quantum mechanics does not understand quantum mechanics." So I say this to encourage those of us who find it challenging, and maybe that is all of us, that we should not expect this to be easy. On the other hand, we know that it is of interest and that it is a fundamental interest. So perhaps with that cautionary note, I'll turn to our first speaker, known well to us all, Arthur Zajonc, who will lead us through this field.
Thank you very much, John. Good morning, Your Holiness. Your introduction puts me in a very awkward position. Because if I say I understand quantum mechanics, then clearly I don't understand quantum mechanics. And if I don't understand quantum mechanics, why am I here?
Sorry.
The implications of quantum mechanics for our view of reality, that's really the topic we have before us. You know, yesterday, we spent some time talking about our understanding and view of reality in a more conventional, classical sense in the world of physics. Galileo, looking through his telescope, making careful observations, reasoning from those observations to inferences based on his observations and logic. We have done an enormous amount of good work in that regard. But about 120 years ago, physicists who had really worked hard using observation, experimentation, and logic, reasoning, felt that they had come essentially to the end of their subject. I'm going to show just a picture of that community. We tend to think of this community of physicists as must be thousands and thousands of them. And of course now that's true. But in the time of around 1900 to 1927, when this photograph was taken, when the birth of quantum physics took place, it was a handful, a relative handful of people who were thinking the new thoughts, the new physics. And there were, according to one of them, an English physicist by the name of Lord Kelvin, he said, really, we understand everything except two small clouds on the horizon. So the sky was perfectly blue, except for these two small clouds. The one of them, yeah, the one was what I call the color of candlelight. When you light a candle, you see the flame, and the flame has got a particular color. And you can ask yourself, why does it have that color? Now, in the classical physics, you would bring all of your careful understandings of heat, of light, and so forth to this subject. The simple question, light a candle, why is it the color it is? It turns out you can't properly explain that color. You can make measurements, you can pass light through the prism and see its colors, but the distribution of colors, the color of the candlelight, you can't predict. So Lord Kelvin said, this is a problem. Why can't we predict the simple phenomenon of candlelight? The second one is more complicated. You know, yesterday we were talking about sound on the moon and the fact that you needed air in order for sound to propagate. If you take the air out of this room, well, we all would die, but in the middle of that process we would be yelling at each other and we would hear nothing, right? Because there was no air to carry the sound. But if you think about it for a minute, it's also remarkable that on the moon there's no air, but I can see the other astronaut. So I'm taking a photograph, and the light passes through a space with no air. The sound cannot pass through the space, but light can pass through space with no air. So in 1900, physicists asked, well, there must be something still, even without any air. Exactly, because light was considered a wave, just like sound. There must be something waving. Up here you see water, and you can see little waves on the water. Or you can have... It needs to be a medium, a thing, something like air that is waving. That's the logic, yeah? And maybe it's a big wave, like this one. Yeah. But the concept of a wave of sound, a wave of light, seems so logical that when people looked for the medium, the ether it was called, that would carry the light wave, they felt sure they must find it. But they never found it. Even to this day, it's never been found. And so we now believe there is no ether. There is no light-carrying medium. So this is the second experiment that was done. So there are two key experiments. One, an experiment trying to study and understand the color of candlelight. The second, what's the medium that carries light? In order to solve these questions, two new theories were developed. The first is quantum physics, that was connected with the color of candlelight. The second is the theory of Einstein's relativity. When you take the assumptions and calculations of the new physics of quantum mechanics, the color of candlelight can be predicted perfectly. When you understand Einstein's relativity and apply it to space and time, you realize there is no need for a medium called the luminiferous ether. The ether, light can travel without. So that is the birth, you could say, from these two small clouds of two huge theories which change fundamentally change our picture of reality. Now, quantum mechanics is, as Feynman and many have said, very difficult to understand. Its ideas are very counterintuitive, and there are various ways to approach the the understanding of quantum mechanics, I will introduce one concept. Michel Bitbol, my friend and colleague, will introduce others, and gradually we'll build up the key elements of what's necessary to understand this new concepts, these new ideas, and their implications, both philosophical and practical. So we'll look at the question of the principles of quantum mechanics. I'll pick just the one which is already very challenging. I have here two coins. I've put a couple of coins up on the screen so everyone can see. But I have here two coins, two, in my case, 5 rupee coins. Up there, there are 10 rupees. The question is, well, it's a kind of a stupid question. How do you know there are two? Well, you can tell them apart because they're located in different places. There's one on the right, there's one on the left. Also, this one has a little scratch. It's a little different than this one. They're very similar, but they're not exactly the same. If I try to put them in the same place, I can't put them in the same place. They can't occupy the same volume. But what if the two entities are not coins, but atoms or electrons or what have you? Now in that case, you have a very different situation. The two atoms, whatever atom A and atom B may be, they are absolutely identical. There's no scratch on one. There's nothing that would tell you this is atom A or this is atom B. They're completely twins. Yeah? But you can say yes, but still one is on the left and the other is on the right. But in quantum physics, you have a situation where these two, which are separated, can actually overlap. Yes, just leave it. You leave the slide up. This is a new slide. Okay? Yeah.
Say, for example, the analogy of the two coins.
I think generally, it's atom level, small particle is always moving. So not necessarily same direction. One
the
atom
spin.
go this way, or one another way. So two coins, the same nature because of the composite, this sort of very subtle sort of
Particles.
But each atom is a different
Yes.
way of moving.
Right.
So not exact.
Yeah.
Same.
Well, it turns out that if you have, let's say, a hydrogen atom and a hydrogen atom, two very simple atoms, there is nothing by which you can distinguish them. They're exactly twins.
But what
And-
about their movement? The spin directions. Are
Yeah.
they all exactly the same?
Yes. Let's just say yes. I mean,
Yes.
well, the problem is you're using a classical concept, namely that there's a movement of an electron in a particular trajectory, like you have in these pictures here. This is really a wrong image. You can't imagine. The electron itself has no specific location, and it has no specific trajectory, no path by which it moves. All right? So you have the picture which most people have, that the atom is like a planetary system with planets moving around the sun. That's an approximation, but it turns out to be wrong. The key thing is that they're indistinguishable. Atom A and atom B are exactly the same.
The same exactly the same location.
Yes, the atom of hydrogen.
So what
another
about
second-
the location? Can we say
Okay,
exactly?
now classically, you can't overlap two objects. These two coins
Oh yes. Oh.
cannot. But the two atoms can not only overlap, but can occupy the same place.
Networks.
I think you have to have a different concept of the atom. The atom is not solid in the way in which we normally think. If I think of the warmth of my body,
그냥 that moves 그러잖아요. 다 코로코로야 relatively forward side sloped to
Larin. So the moment we use the notion of movement, then, whatever may be the framework, within that framework we can talk about relative direction.
so one might be moving one way, one might be moving the other way.
Yeah.
수학에 차지다.
Larin.
막수에 차지다.
So in that case, there's anything that has a direction, even though it may be relative, we can speak about its front and back.
Yes, but in quantum mechanics, everything depends on, you could say, not only these principles of identity, but also of observation. Right? If you observe a particular atom, then it becomes a kind of object. All right? But if you don't observe, then there's an ambiguity, a lack of knowledge. Right? Now, normally, in physics or in realities, if you don't observe something, it doesn't matter, right? These two objects are separated, whether I look at them or not. So when you say something is moving, you're presupposing you're observing. Okay, so
Am I right in explaining to you, Solan, the point you are making is that when we think at the quantum level, if we bring in the notions and concepts from the classical physics, then
Exactly.
we run into all these contradictions.
right, exactly.
So we need to have a whole new way of
You have to
thinking.
have a whole new, and I think it's best to go stepwise. So the first is that each of the atoms, say hydrogen atom and 1 and hydrogen atom 2, they're duplicates. They're exactly the same, not like a coin, and they also can interpenetrate. They can overlap, or they can occupy the same volume. These are not possible in classical physics or in normal life, right? Unless, of course, you have special powers.
But then, but given that the quantum mechanics is still called physics, you're supposedly talking about physical reality, aren't you?
Yes, but at a very subtle level. You know,
But one can progressively go subtler and subtler.
yes, and
But are you
you-
suggesting there's a disjunction? There's no.
That's one of the great challenges of quantum physics, right there. How do you go from what is true at the microscopic level? And we know that quantum mechanics is true when you have billions of atoms. We've done measurements which show that that is true. But when does it become like this world, which is so different in its laws and principles? And this is one of the great questions that still exists within quantum physics. And there are arguments, disputes, as to how to understand that transition. So, I'm going to take us one step further. This concept is called indistinguishability. I don't know, is that a
Yeah.
concept in...
예, 예를 들어봐.
임시당도 그래.
나를
차시부터.
임재당부터. Okay.
So atom A or atom B are indistinguishable, or the picture of Your Holiness on the right is indistinguishable from the picture of Your Holiness on the left. Now, I'm going to allow for these two images to overlap, just like the atom. All right, so we can bring them together. Now I'm going to allow them to come apart, but there's an ambiguity because they could come apart this way or they could come apart this way, right? So they could come apart like this, and you're not sure whether when they came together, they continued or they went back. Logic, okay? It's only thinking, but it has huge implications. So there are two options. Here's A and B, and then we bring A and B together, and we can go back to A and B as they were in the beginning, or I can end with B on the left and A on the right. Now I have B, A. So, right, you go like this, or I can go like this. Now,
뒤도 똥으로 뭐더 표기 강도 샤메바.
Solon is wondering to what extent actually those kind of distinctions are purely at the conceptual level or actually at the objective physical level of
yes,
reality.
right. Well, let's stand up and do our little demonstration. We have a demonstration.
Experiment.
Now, what's important in quantum mechanics is that the two objects, John and I, are dressed almost alike, right?
Sorry.
So, but we're going to interact. I can't get inside of him, but we interact, we hit each other, and there are two options. You go back and sit down in your chair. That's one option. The other is that we bump shoulders, we pass by each other, and we sit down.
이제 가져왔어?
Tadi chuni
Okay.
tutugala. Ta ku tube shugulu ya choka wan domar dal ta tamka nyorba. Ye
Okay,
I think that's most difficult part to understand. Yeah,
that's easy.
still Solon is trying to figure out what you are getting at.
You're very patient. Okay. What I'm getting at is the following. What allowed you to make this seem so obvious is that you were watching two grown men, right, acting very silly. And it seemed like you could follow which was going where. Yeah? But now in quantum mechanics, when you have this principle of indistinguishability, the first option and the second option are not distinguishable from one another. It's hidden. When you look at the end and you see John in this chair or me in this chair, then the hidden character disappears. But in the quantum mechanical phase, in the quantum mechanics of this, that is hidden. And when it's hidden from view, then a new possibility arises.
뒤터로 가는 수신 락베
Quantum level ya tatukuyo maris.
So when it's hidden, then we have a new concept, which is called superposition. That you take this and you add it to that, right? You take both possibilities, even though they are logically distinct, and you put them together in a new kind of relationship, a new state of matter, which is not to be understood classically. This is the part which Einstein complained of, and which Feynman said, if you think you understand this, you don't understand this. Because it's a new concept, a concept where it's neither one or the other, but in some sense both, right? So what you have then is when Your Holiness comes together and then they're separated, you actually have to add option 1, which is A on the left, B on the right, with option 2, which is B on the left and A on the right. This is called a coherent superposition state. Now, you'd say, how do you know this is true? Why should this make any difference? Is this just physicists thinking logically and spinning out theories, or is this fact? Is this true? And is it important? I give you just 2 examples to begin with, or maybe 3. Chemistry requires this ambiguity. You know, in hydrogen does not occur as a hydrogen atom alone, it always occurs as a hydrogen molecule, H2. If you ask what's the force that holds them together, It's the force that arises from this so-called ambiguity, this quantum superposition state. That's the covalent bond. So you could say everything around us holds together because of this quantum mechanical confusion. It's not confusion for nature, but for us and our normal logic, this is so powerful that it organizes all of the substances around us. It also creates something we now call quantum holism. I understand there's this concept of Indra's net, where in every place there is an image of every other place. So it's as if there's a jewel. It's as if there's a jewel and it mirrors every other jewel in a net, so that you look into one object but you see all objects. When John and I bumped shoulders, we became what's called entangled. We became connected. And then if you and I bump shoulders, another part of the net is created, and John and I both now become entangled with you. And you and I and John are all now part of this relationship, and then with Jimpa and everyone in the room, right? So you start with a single atom, you connect it to one, it interacts, now it's entangled, and you create this holistic set of relationships, as long as its indistinguishability is still held. So you gradually propagate this, and this kind of holism is now being used for technological purposes. In other words, in the United States, we're very practical. And so the physicists are doing their thinking, and most people are not interested. What difference does it make? But now that we can create computers built on this concept, if this concept were false, then these computers would not operate. If this concept is true, then they can operate. And they can, for certain kinds of problems, calculational problems, very important calculation problems, they can work extremely fast. You know, when you swipe your credit card and it says a secure transaction, it codes your transaction into a secret kind of mathematical expression, sends it, and then it's decoded. And it would take many, many centuries, perhaps even billions of years, to decode that transaction. Such computers, though, have the promise of doing this instantly, essentially instantly, in a matter of seconds. They're very powerful because they have the holism as part of their computational power. Not individuals calculating, but it's as if all of the people in this room, all of their intelligence was reflected holistically into the computer itself. Yeah.
Am I right in understanding this to be some kind of the middle, which defies the law of excluded middle? It's neither A nor B, somewhere in the middle. It's almost like both or...
It's a little more complicated than that still, I'm afraid, but let's say yes for the moment.
For the moment, yeah.
For the moment. I think in this case, the important thing is to think, let's say you want to do an addition or a calculation that's very difficult. If you do it alone, it may take you a long time. If you can break up the calculation into parts and give Jimpa something to do, Christoph something to do, Richie, and each of the people in this room part of the calculation, it'll go much faster because you've divided it up. Now imagine the possibility that all of their intelligences can be put on you, that you enfold, you take all of their capacities and you have that in one place, not distributed amongst many individuals. That's normal parallel computing. But in quantum computation, all of those quantum objects in the world now can be superposed in one quantum register, in one quantum place. So you have one quantum individual with the intelligence of many, you could say. And then when that computation runs, it runs quantum mechanically with all of these entanglements and can provide the answer very quickly. All right? So that's a totally new possibility, and it has been demonstrated to be the case. Anton Zeilinger, who you know in Austria, the physicist, is
다는 오스트리아에 자우지가 다는 퀀텀 피지크스 님은 다른 살을 잡으러 수부 돕지는지.
Right.
in Wien, in Vienna, and prior when we were in Innsbruck together, Anton with the beard and all the hair. Remember him?
네, 네.
Yeah. So he's an expert in this field.
뒤한테 가르치 의외로 단지 증들배.
He's the one who demonstrated
가사님이 이제 살아나다. 소견 맡으시.
Latin. What was
Ticker.
it? What is it
Wave
called?
particle
Double
duality.
slit.
Double slit experiment.
experiment. Latin.
Yes, that's the one,
Double
Your
slit.
Holiness. He had a piece of equipment here. Yes, same person. He's
Because
the
he's
world
six,
expert.
예민했어요, 가서.
Indeterminacy.
말하지 말이야.
Randomness.
가.
Randomness. It random.
랜덤 or 랜덤 샷.
Yeah, he talked about randomness.
Yes, because one of the fundamental characteristics of quantum mechanics is what we call objective randomness, that certain events take place without a cause, yeah? Which you found also challenging at the time. Yes? I think this concept of superposition is so important and so difficult to understand that I'm going to demonstrate it with these four women here. It's the same woman with four hair colors. Now, normally, you have to have one hair color or the other, unless, of course, you have no hair. Then you have the potential for hair color.
Oh yes. But at least you see, you can make different color.
Yeah,
We still have some.
Mine has gotten a little long, I know. Yeah. But here you have four different hair colors on four different women. Well, actually, on the same woman.
Right.
In superposition, you can have all four at the same time. So it's as if all four of these women came to one place. And of course, color in the physics standpoint is talked about as a wave, and of a certain wavelength is one way of speaking about color. So the question is, can you create the most elementary form of light with four hair colors, for example? So can a photon, which is the single smallest unit of energy of light, is it one color? Or can it be two colors, or three colors, or four colors? And the answer is, experiments that I and others have done show that yes, it can be two colors or more. So we tend to think that the properties of
뒤로
things...
가면 쉬워.
라.
뒤로 가면 쉬워.
근데 외국도 참여가래야. 외국직 아니 저 가도 담는다. 가도 니 나왔어. 용적이 여기서 그렇지.
So a single quantum of light can be emitted with two different colors. Or a single quantum of light...
So the source of the light and then the
Light itself.
the light itself, aren't they composed of the same material? Kind
the
of, you know,
source of the light is
the
an
particle.
atom,
Yeah.
which has substance, it has mass.
The light itself also is a
Light
quantum.
itself has no mass, no rest mass.
So in that case, the source of light atom is still almost in classical terms. It's an obstructive. It has It has a spatially obstructive property.
Has a spatially obstructive property, yes. So you can collide those atoms, right? Whereas
Just
light
like-
can pass through.
Like in past.
Yeah.
자상 뒤니 못 찍도 돼도 뭐.
So in that case, if they can collide, and if each of these atoms have spatially obstructive property, you know, because they're so subtle, it may seem as if they're occupying the same space. Can it still be the case that they are
How can they possibly occupy the
the
same
same
space?
space? Yeah.
Yeah, yeah. Here's the way we now think of these particles. take the simplest particle, the electron. All right? It has a very, very small mass. It has what we call charge, which allows a force to act between electrons, so there's a force. But if you ask what's its size, how big is it, now our best view is that it has no size. In other words, there's a kind of location around which there's a center of force given by this by the mass and the electrical and magnetic properties, so that there is a force field. Take a second electron and you bring it close, the forces between them will cause them to deflect, but they can overlap, and with high enough energies they can overlap essentially completely. So you have
So in other words, to use a plain English, it's got no shape.
Under certain circumstances, atoms do have shapes, but it's they're structures which are what would you call it? They're gentle structures. They're not fixed. They're not hard structures. More like clouds. Or think of the body has warmth, and near me, outside of me, there's also warmth, right? So there's a warmth shape, but it's not obstructive, right? When you come closer, then you hit the skin, the flesh, and that becomes obstructive. So the atoms are more like the energy bodies or the warmth body around me. So you have two types of particles in fundamental physics. You have those which are like the electrons and which are more solid and which have obstruction, and those which are like the photon, which are purely able to pass through one another. There's no obstruction at all. Okay, let me go on. Another strange property is that these particles can go two ways at the same time. Right? When you come to a path which has a fork in the road, then you either go to the right or you go to the left. But a single quantum, a single photon, for example, or a single electron, can be sent. If you see on the left-hand side, you see there's a blue dot, and that blue dot can go both ways. So the single object doesn't split in half. That's a hard thing, again, to understand, but it goes into, again, a superposition state.
Simultaneously.
Simultaneously, it goes into a new kind of state, right? You shouldn't really think of it following a real trajectory, but you should think of it goes into a new state which is ambiguous, but which corresponds to both possibilities.
How can this single atom, one can talk about... So this is basically a simple, indivisible...
Right, quantum.
So it's one thing to say that you can talk about indeterminate,
exactly,
path.
Right.
So that state can be understood.
Yes.
But how can then make the jump and say that it actually goes through both?
Yeah, right.
Because
what's the evidence?
Because when we always said that it's a simple indivisible. So
yes.
It's not splitting into two.
Right. So if you have, there are experiments. If you set up this experiment, as I've done.
So what about that it goes into both parts, but then
moment become two. Now again, you see, become one.
Do they collapse into one? Can one conceive the possibility that it goes in through the both paths by splitting and then collapse?
Yeah. So this is the wave-particle duality. This is what Anton was showing you, all right, when you were doing the experiment on the desk. If you take that single indivisible particle and you put it into this, what we call beam splitter, you put it into a divider in two paths, you could say, well, maybe it goes one way or maybe it goes the other way. Yeah, half the time it goes to the right, half the time it goes straight ahead. Yeah. And then you measure. And if you measure and ask that question, then you, in fact, always find it goes one way or the other way. But if you don't ask the question which way, and you leave that ambiguous
진짜래.
and bring them back together, then you see a phenomenon which can only be understood by going both ways, namely a wave-like interference effect.
Momentarily changing.
Pardon me?
It also momentarily changing.
Is it also in
Changing
motion?
from, yes, it's in motion. Yes, but the direction is ambiguous. But it's ambiguous again in a different way. You know, if I take two coins, and one is a 5 rupee coin and one is a 1 rupee coin, if you close your eyes for a minute, and I give you one of the coins,
I mean,
no, look, don't look. No cheating. And you don't look, then you don't know which coin is in your hand. If you look, you can look at your coin, Your Holiness.
누구 누구한테 말해?
But can't you
Oh,
just
he's
feel it? Yeah.
You're looking with your fingers. Okay, but what coin do you have?
Or maybe
Smell?
some distinction.
some distinction.
right?
What coin do you have?
거기는 고문가 들으셔. 5 rupee. Yeah.
Yes. So,
So 5 rupee coin? Well, if there was a 5 rupee coin and a 1 rupee coin, then which one do I have? I have the 1 rupee coin. It's logic, right? So in the quantum mechanical case, as long as you do not look, there's this ambiguity. In classical physics, it's always the case that there really is a 5 rupee coin here and a 1 rupee coin there. But it could be like with John, you could have the 1 rupee coin and I could have the 5 rupee coin. In quantum mechanics, that ambiguity becomes a powerful reality. It actually is not just ignorance, right? But is actually a positive state, a superposition state. Again, indistinguishability.
아,
스텝